Welcome to Sleepy Astronomy, where space slows down and your mind can rest. Tonight, we're going on a quiet journey to the farthest place we can possibly imagine, the edge of the universe. Before we begin, let us know where you're watching from and what time it is for you. Then get cozy, take a deep breath, and let your thoughts drift away. The universe is big. So big that light from the most distant galaxies takes over 46 billion years to reach us. That's what scientists call the observable universe, the part we can see. But that's not where the universe ends. It just means light from farther away hasn't had time to reach us yet. So what's out there, beyond the edge of what we can see? More stars, more galaxies, or something completely different? In this video, we'll explore one of the biggest mysteries in science. What's waiting at the edge of the universe? The observable universe is the part of the entire cosmos that we're able to see and study using our tools and technology. It stretches out in every direction from our planet, forming an enormous bubble of space that includes everything light has reached us from since the universe began. This bubble isn't small, it's unimaginably huge. But it's not the whole universe. It's just the part we can observe, limited by how far light has travelled since the very beginning of time. You can think of the universe like a balloon that's always getting bigger and bigger. If you're standing on the surface of that balloon, the observable universe is like the part of the balloon you can see from your spot. Everything beyond that is still part of the balloon, but it's out of sight, for now. To figure out how big this observable universe is, scientists use the speed of light as a kind of ruler. Light travels incredibly fast, about 300,000 kilometers every second. But even at that speed, it still takes time to reach us. When we look at a star that's, say, 10 million light years away, we aren't seeing it as it is today. We're seeing it as it looked 10 million years ago, because that's how long the light took to get here. By knowing how fast light travels and how far away different objects are, astronomers create a huge sphere around us that includes all the galaxies, stars, and cosmic structures we can detect. Beyond that invisible boundary, there may be much more, but light from those regions hasn't had time to reach us yet. This measurement isn't simple. It involves detailed calculations, careful observations of distant galaxies, the ancient glow left over from the Big Bang, and how space itself is expanding over time. By piecing all of this together, scientists learn more about how the universe is built, how old it is, and what forces are making it grow. Our understanding of the universe has grown tremendously over thousands of years. In ancient times, people believed Earth was the centre of everything, and that the stars and planets all moved around it in perfect circles. This idea, called the geocentric model, lasted for many centuries. Then, during the 16th century, a scientist named Nicholas Copernicus changed everything. He suggested that the Sun, not the Earth, was at the centre of our solar system. This idea, known as the heliocentric model, completely transformed the way people thought about the universe. Not long after, in the early 17th century, Galileo Galilei used one of the first telescopes to look into the night sky. He discovered moons orbiting Jupiter, proving that not everything revolved around the Earth. The universe suddenly felt much bigger and much more complicated. Fast forward to the 20th century, when even more powerful telescopes were built. In the year 1929, astronomer Edwin Hubble discovered that galaxies are moving away from each other. This meant the universe is expanding, which also suggested that it must have had a beginning. This beginning became known as the Big Bang, a moment when everything in the universe started from a tiny, hot and dense point nearly 14 billion years ago. Later discoveries, such as the faint afterglow of the Big Bang, called cosmic microwave background radiation, gave scientists strong proof that this theory was correct. They also noticed that galaxies are not spread out evenly, but form enormous clusters, long chains, and web-like structures across space. Now, with advanced instruments, scientists have discovered that the observable universe is filled with more than 2 trillion galaxies, and each of those galaxies holds billions of stars, many of which likely have planets orbiting them. Our universe is not standing still. It's growing faster and faster over time. This strange behaviour is caused by something mysterious called dark energy, which pushes space itself to expand more rapidly. We've also learned about dark matter, a type of invisible matter that doesn't give off light or energy, but still has gravity. It helps hold galaxies together and affects how they move. Though we can't see dark matter directly, we know it must be there because of how it influences other things. To study the universe, scientists use many kinds of tools. The most basic one is the telescope. Telescopes gather light and make distant objects appear closer and clearer. Optical telescopes let us see things like stars and galaxies in visible light, while radio telescopes detect radio waves that many cosmic objects give off, even if they're invisible to the naked eye. There are also space telescopes like the Hubble Space Telescope, which orbits above Earth's atmosphere. Because it's in space, it can take clearer and sharper pictures than ground-based telescopes, without clouds or air getting in the way. Some space telescopes can see in infrared or ultraviolet light, allowing scientists to observe even more of the universe. On Earth, huge observatories with powerful mirrors and cameras help us gather more data. Even though our atmosphere can blur images a bit, these observatories still play a huge role in studying the cosmos. Beyond telescopes, computers are essential too. Scientists use special software to process the massive amounts of data they collect, helping them analyze and even reconstruct images of faraway galaxies. Artificial intelligence and machine learning are now helping to find patterns in the data, revealing things humans might miss. In recent years, scientists have also built tools that can detect gravitational waves, tiny ripples in space and time caused by cataclysmic events like black holes crashing into each other. These waves give us a new way to listen to the universe instead of just looking at it. The speed of light is incredibly important in astronomy. Although it moves very quickly, about 300,000 kilometers every second, it still takes time to travel. When we look at distant galaxies, we're actually looking back in time. For example, if a galaxy is located 10 billion light-years away, the light we see from it today left that galaxy 10 billion years ago, long before our planet even existed. This delay means we're looking at a kind of cosmic history book whenever we observe the sky. As the universe keeps expanding, galaxies get farther and farther away. When this happens, the light they send us stretches out, shifting toward the red end of the light spectrum. This is called redshift, and it helps scientists understand how fast things are moving away and how far they are. Because of this time delay, our picture of the universe is not a snapshot of how things look right now, but a glimpse into how they looked long ago. The farther away something is, the further back in time we're seeing. Figuring out how old and how big the observable universe is takes a lot of clever thinking. Scientists study the light from very distant galaxies to see how fast they're moving away from us. This tells us how space itself is stretching over time. They also study the cosmic microwave background, the faint glow from the early universe, left over from just after the Big Bang. This glow is like a fingerprint of the universe's birth, and by analysing it, scientists can estimate that the universe is about 13.8 billion years old. The size of the observable universe depends on how far light has been able to travel since that time. Since the universe has been expanding the whole time, that distance is enormous. The diameter of the observable universe is currently estimated to be more than 93 billion light-years across. Combining all this information, from how galaxies move to the light from the early universe, gives scientists a clearer picture of the universe's age, size, and structure. It's a constantly evolving puzzle, but each piece we discover brings us closer to understanding where we came from and how the cosmos works. At the farthest edge of the part of the universe there is an invisible line, like a horizon in space. This line marks the limit of what we're able to see. Beyond it, the universe keeps going, but it's hidden from us because its light hasn't reached us yet. This is because ever since the universe began, it has been stretching and expanding, causing many galaxies to rush away from us so quickly that their light hasn't had enough time to get here. Think of standing on a huge beach that goes on forever. The ocean spreads out in every direction, but your eyes can only see as far as the horizon. Beyond that line, there are more waves, more water, maybe even islands, but you can't see them because they are too far. The observable universe is like that beach view. It shows only what light has had time to bring to our eyes since the beginning of time. The part of the universe we can observe is truly massive. It spans about 93 billion light-years across. Inside it, there are billions upon billions of galaxies. Each galaxy is packed with stars, some like our Sun, others much bigger or smaller, and many of them have planets orbiting around them. But scientists believe that outside this observable bubble, there is even more universe, possibly many more galaxies, maybe even other regions with strange physics or different kinds of matter. It's a humbling thought. We can only see a tiny portion of what's really out there. This mystery makes us wonder, what lies beyond that unreachable edge? Is the universe endless, or does it wrap around somehow? These questions stir curiosity and drive scientists to search for answers, always trying to go farther and understand more. To figure out how far we can see, scientists study light. Specifically, they look at how far light has travelled since the universe began. Imagine blowing up a balloon. The surface of the balloon grows and stretches out just like space. The part of the balloon you can see is like the observable universe. It's where light has had enough time to reach us since everything started. Scientists believe the universe began around 13.8 billion years ago with an enormous explosion known as the Big Bang. Since then, light from the earliest stars and galaxies has been travelling across space. Light moves very fast, about 300,000 kilometers every second. But because the universe keeps expanding, the distances it has to cover also keep growing. That means the light from the most distant objects we see today started its journey billions of years ago, when the universe was still very young. The farthest light we can detect today comes from extremely ancient objects. This forms what scientists call the cosmic horizon, the edge of our visible universe. It's not a physical wall, it's more like a limit of how far back in time we can look. No matter how good our telescopes become, we will always be limited by how old the universe is and how fast light travels. Some parts of space are simply too far away for their light to have reached us yet. One of the most important pieces of evidence about the early universe comes from something called the cosmic microwave background radiation, or CMB for short. This is the oldest light we can see, a faint glow that fills the universe like an invisible fog. It's a remnant from a time when the universe was only about 380,000 years old, just a baby compared to its age today. Think of the CMB as a snapshot of the universe when it was still very young. It shows us what the universe looked like just after it became cool enough for atoms to form and light to move freely. It's like looking at a baby picture of the universe, fuzzy but incredibly valuable. This ancient light is spread out evenly in all directions and has almost the same temperature everywhere, which tells us the early universe was very smooth and uniform. But if we look closely at the CMB, we see tiny changes in temperature, small bumps and dips. These tiny differences show where matter was starting to clump together. Over time, those clumps became galaxies, stars, and planets. So, in a way, the CMB is like a treasure map, showing the early seeds of everything we see in the universe today. The CMB doesn't show us the edge of the universe itself because we don't even know if the universe has an edge. But it does show the limits of what we can observe from the early days. The light from the CMB has been travelling for over 13 billion years to reach us. That means we're looking far into the past, through a small window in time, giving us a glimpse of how it all began. This radiation is not just interesting, it is essential. It helps scientists figure out how the universe has grown and changed over time. It supports the theory that the universe went through a fast and powerful growth spurt early on, a period known as cosmic inflation. That sudden expansion helps explain why the universe looks so similar everywhere we look. To understand how galaxies and stars are moving today, scientists use something called redshift and blueshift. These are changes in light that help us know whether an object is moving away from us or toward us. It works a bit like sound. Think about how an ambulance siren sounds higher as it comes toward you, and lower as it moves away. That's called the Doppler effect. Light works the same way. If a galaxy is moving away from us, its light waves get stretched, making the light look redder. This is called redshift. If a galaxy is coming toward us, its light waves get squished, making the light appear bluer. That's blueshift. By measuring how much the light shifts, scientists can tell how fast things are moving and in which direction. Redshift is especially important because it tells us that the universe is expanding. Almost all distant galaxies are moving away from us, and the farther they are, the faster they go. This discovery changed our entire view of the universe and even helped lead to the idea of the Big Bang. So how do we see all these distant galaxies and faint signals? That's where telescopes and space missions come in. Telescopes are like giant eyes that can see far into space. Some are on Earth, while others are placed on satellites and sent into space. These tools can collect light, X-rays, infrared rays, and other types of radiation that travel from stars, galaxies, and other cosmic events. Telescopes don't just show us pretty pictures, they reveal the past. Because light takes time to travel, looking deep into space is like looking back in time. When we see a galaxy that is 10 billion light-years away, we're seeing it as it was 10 billion years ago. Telescopes help us understand how stars were born, how galaxies grew, and how the universe itself has changed over billions of years. Space telescopes like the Hubble Space Telescope and the James Webb Space Telescope go even further. Hubble has shown us galaxies forming, stars exploding, and clusters of stars colliding. James Webb, launched more recently, is looking deeper into space and further back in time than ever before, capturing light from some of the first galaxies that formed after the Big Bang. These incredible machines help us explore the universe's edge, even though we can never touch it. Every new image brings more questions, more ideas, and more wonder. Far beyond the observable universe lies a mysterious realm that continues to stir our curiosity and stretch the limits of our imagination. Scientists believe that what we can observe is only a small portion of a much larger, possibly infinite reality. Like standing on the shore of a vast ocean, we can only see to the horizon, but we know there is far more beyond it. The observable universe is the section of space from which light has had enough time to reach us since the birth of the universe, nearly 14 billion years ago. But space doesn't end there. It keeps going, possibly forever. And what lies beyond that cosmic horizon is a grand mystery. One fascinating idea is that our universe might be just one of many, part of what scientists call a multiverse. This theory suggests there could be countless other universes out there, each one floating in an enormous sea of existence like bubbles in a cosmic foam. These other universes might follow completely different rules. In one, gravity might be stronger. In another, stars might never form. Some could even hold strange forms of life, or none at all. If the multiverse is real, then our universe is just one small corner of a much larger and far stranger reality. Another possibility is that space beyond what we can see is simply more of the same. Galaxies, stars, and planets stretching on endlessly. These distant regions might look a lot like what we see around us, but they're too far away for their light to have reached us yet. Given enough time, millions or even billions of years, some of these regions might eventually become visible, expanding the edge of our cosmic map. Some scientists propose that beyond the observable universe, space-time itself may be in a wild and unsettled state. These far-off zones could be cloaked in what we might call a cosmic fog, where the rules of physics as we know them begin to break down. It might be a place where new dimensions exist, where time flows differently, or where space is still forming, chaotic, unpredictable, and utterly alien to anything we understand. There are also bold ideas that suggest other universes or faraway regions might not be just a little different, but completely unrecognizable. In these places, light might not travel the same way, time might not move in a straight line, or matter might behave in ways that defy all current science. These possibilities make us question the very nature of reality itself. Many of these mind-bending ideas come from attempts to understand how our own universe came to be. One key concept is called cosmic inflation. According to this theory, just after the Big Bang, about 13,800,000,000 years ago, the universe expanded at an unimaginable speed, far faster than the speed of light. In a tiny fraction of a second, space stretched from something smaller than a single atom to a vast, smooth, and flat cosmos. This rapid growth explains why the universe looks so uniform today, no matter which direction we look. But inflation might not have happened just once. Some scientists believe that this rapid stretching of space could happen over and over again in different regions, like popcorn kernels popping in a cosmic microwave. Each pop could create a new universe, separate from our own, each with its own beginning, its own physics, and its own future. This is one of the main ideas behind the multiverse. Quantum mechanics, the science of how tiny particles behave, also adds fuel to the multiverse theory. In the strange world of the very small, particles can exist in many states at once. Only when we measure them do they seem to choose one outcome. Some scientists think that every time a particle chooses, the universe splits, creating a new path for every possibility. That means every choice you make could spawn a new universe, where a different version of you follows a different path. Another theory comes from a complex idea called string theory, which tries to combine the rules of gravity with quantum mechanics. According to string theory, everything in the universe is made from tiny vibrating strings of energy. Depending on how they vibrate, they create different particles and forces. These strings might also require more dimensions than the 3 of space and 1 of time that we're used to, possibly up to 10 or 11 dimensions. These extra dimensions could be hiding other universes with their own physical laws. Some of these guesses rely on the effects of mysterious substances like dark matter and dark energy. Dark matter is an invisible material that makes up most of the mass in galaxies. It doesn't shine or reflect light, but we can tell it's there because it pulls on stars and galaxies with gravity. Without it, galaxies would fly apart. Dark energy, on the other hand, acts like a strange force that pushes the universe apart. It's the reason why galaxies are speeding away from each other faster and faster over time. Together, dark matter and dark energy form most of the universe, more than 95% of it, in fact. That means everything we can see, stars, planets, dust, gas, is only a tiny sliver of what's really out there. The idea of a multiverse is one of the most mind-blowing concepts in modern science. It suggests that our universe, the one we live in with stars, planets, galaxies, and all the laws of physics we know, might not be the only one. In fact, there could be an endless number of universes, each with its own unique features, rules, and possibly even different forms of life. Think of a vast cosmic ocean, stretching endlessly in every direction. Now imagine this ocean is filled with countless bubbles, floating side by side. Each of those bubbles represents a separate universe. One of them is ours, the rest? They could be wildly different. Some might be very similar, with stars and people like us, while others could follow completely unfamiliar laws of nature, where even the concept of time or matter could work differently. This idea doesn't come from wild imagination alone. It's rooted in serious science, from quantum mechanics to cosmology and string theory. Let's start with quantum mechanics. At the tiniest level of reality, where atoms and particles live, things don't behave in ways we're used to. A particle can exist in multiple states at once, like it's in many places at the same time, until someone observes it. Some scientists believe that every time a choice is made or an event happens, the universe might split. One version goes one way, another version goes the other way. This could lead to a vast number of branching realities, where everything that could happen does happen, just in a different universe. Now consider the story of how our universe began. After the Big Bang, which happened around 13.8 billion years ago, the universe expanded very quickly, in a flash. This is called cosmic inflation. Imagine blowing up a balloon super fast. In that instant, different regions could have expanded at different rates, creating bubble-like pockets in the fabric of space. Each of these pockets could be a universe of its own, floating in a grander space known as the multiverse. Some of these bubble universes might bump into each other. If they do, strange things might happen. We might see unusual bursts of energy, or new particles could suddenly appear in our universe. In other cases, bubbles might just drift by without ever touching. If they do collide, they could even form a brand new universe, unlike anything before. One of the most exciting theories connected to all this is called string theory. It suggests that the basic building blocks of everything, not just atoms but even electrons and protons, aren't little dots. They're actually tiny vibrating strings, much smaller than we can see. Like the strings of a guitar, these microscopic strings can vibrate in different ways. Each kind of vibration creates a different particle. For string theory to make sense, though, the universe must have more than the 4 dimensions we experience, 3 of space and 1 of time. Some versions suggest there could be 10, 11, or even more dimensions, but we don't see them because they might be curled up so small they're hidden from us. Experiments in particle accelerators, like the Large Hadron Collider, are trying to find signs of these extra dimensions. When particles smash together at near light speed, they might behave in ways that hint at forces or dimensions beyond the ones we know. Even the way gravity works on stars and galaxies might offer clues that unseen dimensions are tugging at the universe in subtle ways. Although these ideas sound like science fiction, they are taken seriously by many scientists because they come from real mathematics and observations. And speaking of science fiction, books, films, and shows have long loved the idea of other worlds beyond our own. These stories often show fantastical alien civilizations, strange new worlds, or technologies far ahead of ours. Whether it's jumping through wormholes to new galaxies, or discovering a mirror Earth in another universe, these tales capture our deep human desire to explore the unknown. They also let us explore big questions. What if there are other versions of ourselves out there, living different lives based on different choices? What if entire civilizations rose and fell in a universe with entirely different rules? What if life can take forms we've never even imagined? Popular culture uses these stories not just to entertain, but also to make us think about who we are, about how we fit into the cosmos, and about the possibilities beyond the stars. The strange landscapes, mysterious creatures, and grand adventures on screen can reflect our own world too, serving as metaphors for our hopes, fears, and challenges. However, the idea of the multiverse, though still unproven, opens our minds to the incredible possibilities of existence. At the farthest edges of the observable universe, there are breathtaking and mysterious cosmic wonders that show us just how enormous and complex space truly is. You can think of the observable universe like a giant invisible bubble surrounding Earth. This bubble stretches out across space in all directions, reaching as far as light has travelled since the beginning of time, which scientists believe began around 13.8 billion years ago. But this outer edge isn't a wall or a barrier, it's more like a horizon, a limit to what we can see. Beyond it, the universe may go on forever, but its light hasn't had enough time to reach us yet. One of the most incredible discoveries at this boundary is the cosmic microwave background radiation, often called the CMB. This is a very faint glow that fills the entire universe. It's not ordinary light that you can see with your eyes. It's more like a soft whisper of warmth, coming from a time almost 14 billion years ago, just a few 100,000 years after the Big Bang. Back then, the whole universe was a hot, dense fog of particles, like a cosmic soup. As the universe cooled down and expanded, this light was released, and it has been travelling ever since. The CMB is like a baby photo of the universe, showing us what things looked like when everything was still young. It holds secrets about how everything began and what conditions were like in those very first moments. As we look farther and farther into space, we see galaxies that are moving away from us at mind-blowing speeds. This is because the universe is expanding, not like things flying through space, but like space itself is stretching. The more distant a galaxy is, the faster it appears to be moving away. Some galaxies are so far that their light will never reach us, no matter how long we wait. This means there are whole parts of the universe, full of stars, planets, and energy, that we will never be able to see. At the edges of this visible realm, we also find something called redshift. When light travels through expanding space, its waves get stretched out, shifting the light toward the red side of the spectrum. So, when we look at faraway galaxies, they appear redder than they really are. The farther the galaxy, the more redshifted its light becomes. This redshift helps scientists figure out how fast the universe has been growing over billions of years. But the edges of the observable universe are not just distant and quiet. They're filled with gigantic structures still taking shape. There are newly forming galaxies, enormous strands of matter called cosmic filaments, and giant groupings of galaxies known as clusters. These structures are shaped by gravity over unimaginable stretches of time, millions and even billions of years. They are part of the ever-changing cosmic dance that has been unfolding since the dawn of time. Among the most mysterious objects near these far-off regions are black holes and quasars. A black hole is a place in space where gravity is so powerful that nothing, not even light, can escape from it. This makes black holes invisible, but we can spot their presence by watching how matter behaves around them. When gas or dust falls into a black hole, it forms a swirling disk called an accretion disk, which gets incredibly hot and shines with enormous energy just before vanishing. This glowing material tells us that something invisible and immensely powerful is lurking there. Quasars are some of the brightest objects in the universe, even brighter than entire galaxies. They are powered by gigantic black holes sitting in the hearts of galaxies. As matter falls into these supermassive black holes, it gives off dazzling light and energy. Many of the quasars we see are located billions of light years away, meaning their light left them when the universe was still young. By studying quasars, we can peer into the early history of the cosmos and see how galaxies looked and behaved billions of years ago. Black holes and quasars also suggest that there might be even more out there. Vast areas of space still hidden from our view, filled with unknown forces and invisible structures. These mysteries encourage scientists to keep pushing farther, to explore beyond the limits of what we can currently observe. In addition to these exotic objects, the universe is built on massive structures called galactic superclusters. These are the largest known formations in the universe. Imagine the cosmos as a huge web, and in this web, galaxies are like shining beads, connected by long threads. Superclusters are the cities of this cosmic landscape, each one holding hundreds or even thousands of galaxies grouped together by gravity. These galaxies are connected not only by their own weight, but also by dark matter, an invisible kind of mass that doesn't shine or glow but helps hold everything together. Superclusters shape the flow of matter through the universe. Think of them like cosmic highways. They guide how galaxies move, where they gather, and even how they evolve over time. By studying how superclusters formed, astronomers learn more about the history of the universe and about dark energy, a strange force that causes the universe to expand faster and faster. Surrounding and separating these superclusters are enormous cosmic voids, vast regions with very few galaxies. These are the quiet, empty spaces of the universe. Between them stretch the cosmic filaments, the bridges of matter that connect galaxy clusters together. This web-like pattern of voids and filaments shapes how galaxies form and move. It even bends and twists the light from faraway galaxies, changing how we see them from Earth. Studying voids helps scientists understand how fast the universe is expanding, because these empty spaces are growing more quickly than the crowded areas filled with galaxies. By mapping out these filaments and voids, we can build a three-dimensional map of the universe and uncover the forces that control its structure. Beyond all this, there are even deeper and more mysterious forces at play. One is dark matter, which makes up most of the universe's mass. We cannot see it or touch it, but we know it's there because of the way galaxies move. Without dark matter, galaxies would not hold together. They would simply spin apart. Dark matter acts like an invisible skeleton, holding up the structure of the universe. Then there is dark energy, an even stranger force that pushes galaxies apart, speeding up the expansion of the universe. While we still don't fully understand what dark energy is, we can clearly see its effects. It's as though the universe is not only expanding, but accelerating as it does so. Some scientists believe there may be more dimensions beyond the three we live in: length, width, and height. These extra dimensions might contain entirely different physical laws or even parallel universes, with their own versions of stars, galaxies, and possibly life. And even in the emptiest parts of space, there are quantum fluctuations, tiny bursts of energy that flicker in and out of existence. These microscopic events suggest that even nothingness isn't truly empty. There may be deeper layers of reality beneath what we can measure, hidden worlds of energy, particles, and laws we have yet to discover. Studying how the universe began is like uncovering the opening chapters of the greatest story ever told. A story that explains not only how everything around us came into existence, but also how it has grown into the vast and majestic cosmos we see today. Scientists, like cosmic detectives, explore this ancient tale by investigating one of the most important events in all of history, the Big Bang. The Big Bang marks the moment when time, space, matter, and energy first appeared. This happened around 13.8 billion years ago. In that instant, the universe began expanding from an unimaginably hot and dense state. From that starting point, everything else, galaxies, stars, planets, and even life, slowly took shape over billions of years. One of the most important tools scientists use to understand those early moments is the cosmic microwave background radiation. This is like a faint invisible glow that fills the universe, an afterglow of the Big Bang itself. By carefully examining this ancient light, scientists can learn how matter and energy were arranged in the beginning. That early arrangement influenced how galaxies later formed, creating a huge cosmic web of stars, gas, and dark space. Some areas became crowded with galaxies, while others remain almost completely empty. But understanding the layout of the universe isn't enough. Scientists also measure how fast the universe is growing. Since the Big Bang, space itself has been stretching like an inflating balloon. The faster this expansion happens, the more it tells us about the size and age of the observable universe, the part we can see using telescopes. Beyond that, however, there may be much, much more. The more we discover about how the universe began, the more we realize just how enormous and mysterious it truly is. Every piece of knowledge is like a thread woven into a vast cosmic tapestry, and with each thread, we see more clearly where we fit in the universe and how much more lies beyond what we can currently see. Theories about the Big Bang say the universe began in a very small, incredibly hot and tightly packed state. Then it expanded rapidly. But as we look around the night sky, we can only see a small part of the full universe. This visible part is known as the observable universe. You can think of it like peering out of a tiny window. You can only see what's directly in front of you, while the rest remains hidden. Many scientists believe that the universe is much bigger than the part we can observe. In fact, it may even be infinite. Beyond the limits of what our telescopes can detect, there could be countless stars, galaxies, and even other strange cosmic events unfolding right now. These distant regions may look just like our part of the universe, or they may be totally different. Some theories even suggest that faraway parts of the universe might follow different physical rules, such as different types of gravity or matter. One reason we can't see these areas is because light travels at a limited speed. Since the universe began, only a certain amount of light has had time to reach us. That's why we can't observe places that are too far away. Their light hasn't gotten here yet. But over time, as more light reaches us, we may be able to see deeper and farther into the universe. However, there are also some parts of the cosmos that we may never be able to see. These places are moving away from us so quickly that their light will never reach us, no matter how long we wait. That means entire regions of the universe will remain permanently hidden from us, a mystery we can only imagine through science and theory. The idea that the universe might be much more complex than it appears is not new. Some scientists even propose that beyond what we can observe, the universe might be split into regions with completely different laws of nature. These ideas lead to incredible questions. What if there are other types of life out there, surviving in environments completely different from Earth? What if there are multiple universes, each with its own version of space, time, and physical reality? This brings us to the idea of cosmic evolution, the grand process through which the universe has changed and developed over time. It started with the formation of the first atoms, then stars, then galaxies. The observable universe is simply the portion we can see based on how far light has travelled since the Big Bang, which was about 13.8 billion years ago. But beyond that, the universe might keep going forever. As the universe continues to expand, faraway galaxies move farther and farther away from us. Just like when you blow air into a balloon, and the dots on its surface move apart, galaxies drift away from each other over billions of years. Because of this, some parts of space are now so distant that the light they emit will never reach us. Those unreachable regions are like unopened pages in the story of the universe, chapters we know exist, but may never read. Still, even in areas we can't see, cosmic evolution continues. New stars are born, old galaxies collide. Mysterious phenomena may unfold in silence. Though we may never witness them, we know the universe's story doesn't stop at the edge of our vision. Another powerful idea that helps us understand the universe is cosmic time. This is like a giant universal clock that started ticking at the moment of the Big Bang. As the seconds, minutes, and billions of years tick by, scientists use cosmic time to organize the events of the universe, from its blazing beginning to the complex web of stars we see now. When scientists look at distant galaxies, they are looking back in time. That's because light from faraway objects takes millions or even billions of years to reach us. So, when we observe a galaxy that is 10 billion light-years away, we're seeing it as it was 10 billion years ago. Cosmic time helps scientists build a timeline of the universe's history and understand how everything fits together. Cosmic time also shows us how the universe is changing. As time goes on, galaxies move farther apart due to expansion. By studying this, scientists can predict how the universe will continue to grow in the future. In this way, cosmic time helps us explore the past, measure the present, and imagine the future of the cosmos. And then there is one of the most exciting questions of all. Are we alone in the universe? The search for extraterrestrial intelligence, that is, intelligent life beyond Earth, opens up a thrilling new chapter in our understanding of the universe. If we were to discover such life, it would change everything. It would mean that Earth is not the only place where life can thrive. Alien civilizations might live under conditions completely different from those on our planet. They might have developed amazing technologies, new ways of thinking, and entirely different perspectives on life, time, and space. If we studied them, we could learn better ways to use energy, understand new types of communication, and gain insight into the deeper rules of science and biology. If these civilizations have already explored the stars, their methods could help us travel farther into space. They might show us how to survive in harsh environments, or reveal new aspects of the universe that we've never considered. In short, discovering extraterrestrial life would not just confirm that we're not alone, it would expand our vision of what is possible. It could also help us look at our own world in new ways. Their experiences might offer solutions to Earth's problems and encourage us to work together more peacefully as a species. In the end, learning about life beyond Earth might teach us more about ourselves, where we come from, how we fit into the universe, and what kind of future we want to build. So, from the first brilliant flash of the Big Bang to the possibility of alien life, the story of the universe is one of endless wonder, constant change, and infinite questions. Every new discovery takes us one step closer to understanding the breathtaking scale and beauty of the cosmos. For many years, humans have eagerly searched the wide stretch of space, hoping to find even the faintest sign that we're not alone in the universe. Using the most modern telescopes, we watch the stars and planets without stopping, our hearts beating fast with the chance of finding something amazing. We listen carefully, waiting for any signal that might show the presence of a life form from another world. Yet, for the most part, space answers our efforts with nothing more than the strange silence of the universe, broken only by the far-off hum of pulsars or the soft static of the cosmic microwave background radiation. But then, on August 15th, 1977, something happened. For the first time in history, a signal from space was found that was unlike anything scientists had seen before. It was a clear, strong radio wave that seemed to be a sure sign from beyond our planet, a clear and purposeful message from somewhere in the universe. This signal stood out so clearly from the usual space noise that Dr. Jerry Eyman, who was part of the team at the Big Ear radio telescope, felt the need to act right away. Happily, he circled the strange signal on his printout with a red pen, and without much thought wrote, "Wow," a simple reaction that would always be linked to one of the most confusing mysteries in the search for life beyond Earth. The signal has since been known as the WOW signal, and it has stayed in the minds of scientists, space lovers and dreamers alike for almost 5 full decades. This strange event is still something people find interesting and puzzling, making them ask, could it have been a message from a life form from another world? The signal's short but strong appearance has left many people wondering where it came from and what it meant. In the summer of 1977, the search for extraterrestrial intelligence SETI program was going strong. This effort, which was directly paid for by NASA, was fully focused on looking through space for signs of smart life beyond Earth. The program had been running for several years, and people's hope about the chance of finding proof of alien life was at its highest point. SETI scientists had been using radio telescopes to listen for strange signals from space, hoping to find something that might show the presence of smart beings somewhere else in the universe. At that time, the Big Ear radio telescope located at Ohio State University was the main tool used for this search. For months, the telescope had been gathering information, listening to the white noise of space, an endless static-like hum that filled the wide emptiness of the universe. Despite all their hard work, the scientists had found nothing important. Then, on that unforgettable day in August, the silence was broken. Dr. Iman, working the night shift, was carefully watching the data when he noticed a strange, strong burst of radio waves. This signal was so powerful and so unusual that it quickly got his attention. The strength of the signal was 30 times greater than anything the telescope had picked up before. It was unlike any signal they had ever seen, and it seemed to match exactly what scientists had guessed might be signs from a life form beyond Earth. In that moment of finding something new, Dr. Iman circled the signal and marked it with his now famous word, "Wow." That simple word would come to describe this amazing event, which has since become one of the most well-known and confusing events in the history of the SETI program. The WOW signal came from a part of space in the Sagittarius constellation, a part of the sky that had been closely looked at by space scientists. There was no doubt about where the signal came from. It came from outer space, not from anywhere on Earth. However, despite the excitement around this discovery, the true nature of the signal stayed unknown. Was it really a message from a life form from another planet? Or was it just a rare burst of radiation from some other space event? The signal itself, sadly, did not leave behind any clear proof of what it meant. The Big Ear radio telescope did not record any sounds. Its main job was to measure how strong the radio waves were. The data that Dr. Iman circled on his printout was made up of numbers that showed how strong the signal was. These numbers were part of a system used by the radio telescope to show the level of the radio waves it picked up. Most of the signals the telescope had been picking up until that moment were weak, with values ranging from 1 to 3 on the scale. But the WOW signal was different. It was so strong that the scale couldn't even hold its full strength, and the signal was marked with a mix of letters and numbers to show how strong it really was. The WOW signal did not come with any sound you could hear, and the information gathered by the Big Ear radio telescope was not a recording of a voice or a clear message from a life form from another world. Instead, it was simply a sharp burst of radio waves that stood out from the usual background noise. Even so, the event was important because it was the first time that a signal this strong had ever been found, and it matched the features that scientists had been hoping to find in their search for life beyond Earth. The WOW signal has since been the focus of many studies and guesses. Some people think it could have been a way of talking from a life form on another planet, while others think it might have been caused by some natural event that we still don't understand. Over the years, many different ideas have been shared, from the chance that a satellite bounced radio waves back to Earth, to the thought that the signal came from a faraway star or planet giving off strange radiation. Even with all these ideas, the WOW signal is still an unexplained mystery. No signal like it has been picked up again, and all efforts to find another one like it have not worked. The Big Ear radio telescope, which was once used to search for signals from beyond Earth, was shut down in the early 1990s, and the search for the WOW signal has continued with other radio telescopes and space observatories. However, the WOW signal itself remains a mystery with no answer. In the years after the discovery of the WOW signal, its fame spread, and it became a sign of humanity's ongoing search to understand the universe and our place in it. The recording of the signal itself, often shared on the internet, has inspired many fans and doubters alike, who have studied it very closely trying to figure out what it means. Some have even slowed the recording down, trying to hear patterns or voices hidden in the noise. One such attempt involved slowing down the signal a lot. Some listeners thought they could hear a voice, maybe even a message. In one case, the recording was slowed down so much that it seemed to say, "We lost him at 7 p.m. We've got a 1061. Some people thought this was a police code for stopping a suspicious vehicle. But this idea was proven false when it was shown that the slowed down signal was just a joke, with the sound taken from a police radio and changed to sound like it came from space. The WOW signal is one of the most strange and talked about events in the world of radio space studies. At its centre, it is an amazing signal that seemed to come from deep space, picked up by a big radio antenna pointed at the stars. This antenna, like others like it, is called a radio telescope, which is made to study radio waves coming from faraway things in space. These radio telescopes can be big or small, and while some may stand out against the wide sky, not all of them work perfectly. A good example of this is the Big Ear, which, even though it was special in how it was built, had a few issues that made it less useful than other radio telescopes. The Big Ear itself was huge, about the size of a football field, but the way it looked made it seem unfinished, like a bigger job had been stopped halfway. Even with its size, it couldn't look at the whole sky at once. So how did the Big Ear look at different parts of the sky? The answer is in how it was built. The telescope moved with the Earth as it turned. This let it look at the same part of the sky only once every 24 hours, but only for a short time of 72 seconds. This special way of looking at the sky is one of the reasons the WOW signal lasted exactly 72 seconds. When the WOW signal was found, it followed a very clear pattern. During the first 36 seconds, the signal got louder and louder, reaching an amazing high point, then slowly became weaker during the last 36 seconds. This change in strength was a clear sign that something strange was going on. But the way the signal was found was not very exciting. Unlike what people might think, Dr. Iman and his team were not watching the signal live like the characters in the movie Contact. Instead, Dr. Iman saw the signal's rise only after it had already happened. Even with this late discovery, the real trouble began when the team tried to find the signal again. Even though the WOW signal had been recorded once, no one was able to see it again. The research team tried many more times, asking other radio telescope teams to help find where the signal came from. More antennas were set up in the same part of the sky, but by the time they did this, the source of the signal had already vanished. It became clear that the signal was very hard to find again. Even after many years of trying, scientists could not copy the same setup that led to the finding of the WOW signal. This lack of any follow-up signals only added to the mystery and wonder around it. One of the most exciting things about the WOW signal was that it was different from anything scientists could explain using Earth-based reasons. The signal's frequency, 1420 MHz, was especially important. This frequency was very interesting to space scientists because it is saved for the study of signals from space. In fact, no Earth-based messages are allowed to use this frequency. To be clear, it wasn't just avoided, it was specially kept for space research. Using this special frequency helps explain why the WOW signal caused so much excitement. In the 1950s, a group of scientists including Bernard Oliver, Jep Kone, and Philip Morrison came up with an idea about why this frequency was perfect for possible messages from life beyond Earth. Their thinking was based on the science of hydrogen. Hydrogen, the most common thing in the universe, gives off energy at this exact frequency, 1420 MHz. The idea was that if smart life existed somewhere else in the universe, they would probably use this same frequency to talk. After all, hydrogen is so important to what the universe is made of, it made sense to think that other life forms might also see this frequency as a good place to begin sending messages. Even though this idea was mostly a smart guess, it gave a solid and scientific reason to look for signals from life beyond Earth. So, when the WOW signal was found in the year 1977, it was seen as a big moment in the search for alien life. The frequency it came from was not by chance. The fact that the signal was at 1420 MHz made many people think it could be a message sent by smart beings in space. Because of this, the frequency was kept for future research into life beyond Earth, making sure that no Earth messages would get in the way of finding such signals. But even with all the hopeful signs of the WOW signal, no one was able to track it or find it again. Dr. Iman and his team worked hard to find the signal again, spending many months looking at the same part of the sky, but they had no luck. 10 years later, in the 1980s, another space scientist, Robert Gray, looked at the signal again, trying to get the same results using better tools. He used the Meta array at the Oak Ridge Observatory in the years 1987 and 1989, but again the signal was not found. In the middle of the 1990s, people got interested in the WOW signal again. In the month of July in the year 1995, Paul Shook, the head of the CT League, took another look at the problem while testing new software for finding signals. Using a 12-meter radio telescope at the National Radio Astronomy Observatory in Greenbank, West Virginia, he searched for any sign of the WOW signal. Even with the better tools and his strong efforts, there was still no success. In the years 1995 and 1996, Robert Gray went back to the problem again, this time using an even better tool, the Very Large Array, which was much better at finding weak signals than the Big Ear had been. But even with all these tries and all the better tools, the hard-to-find WOW signal never showed up again. The mystery of the WOW signal is still not solved today, with many scientists still confused by its sudden and strange appearance. What makes it so amazing is not just the frequency it was found at, but also the fact that it came from a place deep in space, with no clear source on Earth. Even though many years have passed since it was first seen, the WOW signal is still a source of wonder and guessing in the science world. For many people, it feels like the closest we have come to finding proof of life beyond Earth. Yet, it is still an exciting mystery that no one has fully explained. In the year 1999, space scientists Gray and Simon Ellingen tried to find the strange WOW signal again, using a 26-meter radio telescope at the University of Tasmania's Mount Pleasant Radio Observatory. They looked 6 times, each time for 14 hours from different nearby places. But even with their efforts, they never found anything like the first signal. These many tries only made the doubters more sure. For years, these repeated failures made them believe that the WOW signal was just a one-time event. Doubters had a hard time coming up with a strong idea for where the signal came from. It wasn't until the year 2017, almost 50 years after the first and only time the signal was picked up, that a possible explanation finally came forward. Antonio Paris, a teacher of astronomy and space science at St. Petersburg College in Florida, said that the signal might have come from hydrogen gas around 2 comets, Comet 266 P. Christensen and Comet 335 P. Gibbs. Between November 27, 2016 and February 24, 2017, about 200 studies were carried out. The results showed that the Christensen comet gave off a sound much like the WOW signal as it got closer to Earth, with nearly the same frequency. More studies on other comets showed the same kind of results. It looked like comets, which give off hydrogen gas that can stretch across millions of kilometers, might make this kind of signal. Even with this idea, many space scientists were still unsure, pointing out problems that made the idea hard to fully trust. There was no solid other explanation for the signal, and no new signals were found in the same part of the sky. But then, in the year 2020, there was new hope. A space enthusiast named Alberto Cavallero made an exciting find. While looking at the part of the sky where the WOW signal was first found, he discovered as many as 15 stars that might be the source of the strange radio signal. Cavallero came up with 2 ideas. First, he thought the signal could have come from a planet like Earth, going around a star like the Sun. Second, he based his guess on the Drake equation, which said that the planet couldn't be closer than 500 light-years from the Sun. To make a list of possible sources, Cavallero used the Gaia telescope's database, which had detailed facts about where stars are and what they're like in our galaxy. He looked at G and K-type stars in the Sagittarius group of stars. These stars had to meet certain rules, like having a size between 0.83 and 1.15 times the size of our Sun. To his surprise, only one star matched these rules, listed as 2Mass19 281982-2687. This star, with a size nearly the same as the Sun, and a brightness 1.7 times that of the Sun, seemed like a good match. Cavallero also found 14 other stars in the same part of the sky that had similar temperatures, but there wasn't enough data about how bright or big they were. Even so, finding this one star was enough to bring back interest in the hunt for the WOW signal's source. Since then, there haven't been any big discoveries, but the search for the WOW signal is still going. The finding of this possible star has brought new excitement to the science world. One day, humans might hear the mysterious signal again, or come across a new one that is just as strange. When that day comes, it could lead to amazing discoveries that change everything for all of humankind. Lately, people have become fascinated not by a signal, but maybe by the very thing we've been looking for in the wide, endless space. In space science, dark matter is a strange and unseen kind of matter that we can't see because it doesn't interact with light or any other kind of energy. We know it is there because of the odd effects it has on gravity, which can't be fully explained by the laws of science unless there's more matter around than we can actually see. These strange effects show up when we study things like how galaxies form and change over time, how light bends around huge objects, called bending by gravity, and even the way galaxies move within groups. We also notice its effect in the shape of the universe and the leftover energy from the Big Bang, the cosmic microwave background. In the most widely accepted idea of the universe, known as the lambda CDM model, the universe's total mass and energy is made up of 5% normal matter, the kind we see around us, 26.8% dark matter, and 68.2% dark energy. That means dark matter makes up about 85% of the total mass, while dark matter and dark energy together make up 95% of the universe's total energy. We don't know exactly what dark matter is, but it doesn't seem to interact with regular matter or light, except through gravity, making it almost impossible to find with our current tools. The top idea is that dark matter might be made up of tiny, unknown particles, such as weakly interacting big particles, WIMPs, or axions. Another guess is that dark matter could be made of ancient black holes from the early universe. Dark matter can be sorted in different ways based on how fast its particles move: cold, warm, or hot. Most scientists think dark matter is cold, meaning its particles move slowly, letting them come together and form shapes over time. While most space scientists believe dark matter is real, some still doubt the idea. A small group of scientists, confused by some things that regular dark matter doesn't fully explain, suggest that maybe the laws of gravity need to be changed. They've come up with other ideas like change Newton rules or new kinds of gravity, but none of these ideas can fully explain all the facts we've found so far. This shows that, even if gravity needs some changes, dark matter still seems to be a needed part of the puzzle. The idea of dark matter has a long and interesting history, filled with surprising findings and ideas that helped build our current understanding of the universe. The story begins with the work of some of the brightest minds in science, starting in the late 19th century. In the year 1884, William Thomson, better known as Lord Kelvin, made some interesting findings. He talked about the possible number of stars near our Sun in a book based on a talk he gave in Baltimore. Kelvin was trying to guess the amount of stars close to the Sun. He did this by looking at how stars move around our solar system. Using this information, he wondered what would happen if there were 1 billion stars within a distance of 1 kiloparsec from the Sun. At this distance, the stars would seem to move in ways that were hard to explain, and this idea helped lead to more thinking about unseen matter in space. Lord Kelvin also guessed the Sun's age to be between 20 and 100 million years, which was later found to be wrong, but his interest in the stars and their motion helped early thoughts on dark matter. A few decades later, in the year 1906, the French math expert and scientist Henri Poincaré used the term dark matter, or matière obscure, while talking about Lord Kelvin's work. Poincaré said that there might be hidden mass in the universe, but he also believed that this hidden matter would be less than the matter we can see. Even though his ideas were far from right, Poincaré's mention of dark matter brought the idea into science talks. In the 1920s, dark matter continued to interest space watchers. In the year 1922, Dutch space expert Jacobus Kapteyn became one of the first to use the speeds of stars to suggest the presence of dark matter. He saw that the way stars move in space could be changed by unseen forces, pointing to invisible matter. Then, in the year 1930, Swedish space expert Knut Lundmark added to the idea, seeing that the universe must have a lot more mass than we could see with our telescopes. This discovery was very important because it showed that the visible universe might not be the full story. In the year 1932, another Dutch scientist, Jan Oort, joined the discussion by saying that dark matter might be in the area around our galaxy. Oort studied how stars move near our galaxy and decided that there must be more mass in our galaxy than was visible. However, he later found out that his measurements weren't fully correct, and more research would be needed to understand what this unseen mass really is. Then, in the year 1933, Swiss space scientist Fritz Zwicky made a big breakthrough while studying groups of galaxies at the California Institute of Technology. Zwicky was looking at the Coma Cluster, a large group of galaxies, and saw something strange. The galaxies in the cluster were moving much faster than expected based on the visible mass. This led him to suggest there was a large amount of unseen mass, which he called Dunkel Materie, dark matter. Zwicky guessed that the Coma Cluster had around 400 times more mass than could be seen through telescopes, based on how the galaxies were moving. He believed that this hidden mass was causing the gravity that kept the galaxies in the cluster together. Although Zwicky's guesses were far off, mostly because of old numbers, he was one of the first to correctly say that the universe must have unseen mass that pulls on things with gravity. Zwicky, however, had a different view of dark matter than we have today. He believed that dark matter was simply ordinary matter that didn't give off light, rather than something completely different, like the strange dark matter we think of today. Still, his work was a big first step toward finding dark matter. As time went on, more proof pointing to the presence of dark matter started to show up. One of the main pieces of this proof came from looking at how galaxies spin. In the year 1939, H.W. Babcock studied the spin of the Andromeda Galaxy, the closest spiral galaxy to us. He found that the stars on the outer parts of the galaxy were moving much faster than expected. This showed that there was a lot more mass in the galaxy than could be seen by just looking at its bright stars. At first, Babcock said that the strange spinning could be caused by light being blocked inside the galaxy, or that the galaxy's motion worked differently in the outer parts. But what he saw was an early clue that something invisible was affecting how the galaxy moved. The next year, in the year 1940, Jan Oort made another important find. He studied a galaxy called NGC 3115 and found a large unseen halo of mass around it. This was another sign that galaxies might have hidden matter beyond what we could see with the tools we had at the time. The idea of dark matter really started to grow in the 1970s. Different scientific finds were brought together to show that galaxies might be surrounded by huge, invisible halos of matter. In the year 1974, two separate research groups, one from Princeton, New Jersey, led by Jeremiah Ostraker, Jim Peebles, and Amos Yahiel, and another from Tartu, Estonia, led by Jani Nasto, Ensar, and Ants Kasich, came to the same idea on their own, making the theory even stronger. One major clue that pointed to the presence of these hidden galactic halos was the way galaxies spin. Both optical and radio astronomy played a big part in these finds. Vera Rubin and Kent Ford, using a new kind of measuring tool called a spectrograph, took more exact measurements of how fast edge-on-spiral galaxies were spinning, and they found strange results in the spinning curves. At the same time, radio astronomers used powerful radio telescopes to study the 21-centimeter line of atomic hydrogen in nearby galaxies. Unlike starlight, which can only be seen from the middle parts of galaxies, hydrogen gas spreads much farther out. This let astronomers look at spinning patterns much farther away, giving them a better idea of how much total mass a galaxy had. Early studies of the Andromeda Galaxy, using huge telescopes like the 300-foot Green Bank telescope and the 250-foot Jodrell Bank dish, showed that the hydrogen spinning curve didn't act as expected based on Kepler's laws, which explain how things should move around a centre of gravity. As tools got better, more sensitive gear allowed for even deeper measurements. In the year 1975, Roberts and Whitehurst pushed the limits, measuring how fast Andromeda was spinning all the way out to 30 kiloparsecs. Their results showed that the galaxy's spinning curve stayed flat even very far out. This mattered because it meant there was a lot more mass out there, beyond what we could see with normal telescopes. These results, shown in their graphs, mixed starlight data with new hydrogen data, clearly showing the surprising flatness of the galaxy's outer spinning curve. The solid line in the graph showed the starlight data, while the other line showed the total mass, which kept going up even in the far edges of the galaxy. At the same time, scientists were coming up with even better ways to study galaxies. Using interferometric arrays, several radio telescopes working together, researchers like Rogstad and Shostak in the year 1972 mapped the hydrogen spinning curves of 5 spiral galaxies. They found that all of these galaxies had flat spinning curves too, meaning that the mass in the outer parts of the galaxies was much higher than what could be explained by bright stars and visible light. By the late 1970s, most scientists agreed that dark matter halos probably existed around galaxies, and this became one of the biggest mysteries in space science. In the 1980s and 1990s, many new observations began to show that dark matter was real. One important study, done by Persic, Salucci and Stell in the year 1996, looked closely at 967 spiral galaxies and found strong proof that dark matter exists. Other proof came from strange effects like gravitational lensing, where clusters of galaxies bend light from things behind them, the way hot gas is spread out in galaxies and clusters, and the way tiny temperature changes, called anisotropies, appear in the cosmic microwave background, which is the leftover glow from the Big Bang. Today, most scientists believe that dark matter is made of particles that we haven't found yet, and these particles are unlike anything we already know. The search to find this strange particle has become one of the biggest goals in particle physics, with many scientists using different tools and tests to try and find the answer. In simple words, when scientists talk about matter in space, they mean anything that adds to the total energy, and its thickness changes in a certain way as the universe gets bigger. It goes down as the cube of the expansion, meaning the farther the universe stretches, the thinner the matter becomes. This is not like radiation, which goes down even faster. Its energy gets weaker as the universe grows, following the opposite of the fourth power of the expansion. But the cosmological constant acts differently. It stays the same no matter how much the universe grows, so its energy amount doesn't change. This difference in how matter, radiation, and the cosmological constant act is because of something called radiation redshift. To picture this, think of the universe growing bigger. If the size of the part we can see doubles, the scale factor of growth also doubles. Because of this, the energy of things like the cosmic microwave background light, the leftover glow from the Big Bang, gets weaker, because each bit of light has to spread over a larger space, which lowers its energy. The same thing happens to super-fast particles like early neutrinos. These also lose energy in a similar way. But the cosmological constant, which is a feature of space itself, doesn't change no matter how much space grows. As for dark matter, this term generally refers to parts of the universe that we cannot see, yet still have mass and obey similar laws to regular matter. However, in more specific terms, dark matter is often used to describe a particular kind of invisible matter that isn't made up of the usual particles we're familiar with, excluding something called missing baryons. Depending on the context, the meaning of dark matter can vary. The arms of spiral galaxies spin around their center, and as you move outward from the center, the visible mass density of the galaxy gets lower. If all the galaxy's mass were visible, it would behave like a simple system where most of the mass is concentrated at the center and objects orbiting it, much like how planets orbit the Sun in our solar system. Based on Kepler's third law, we would expect the speeds of the objects to slow down the farther they are from the center, just like how the planets in our solar system move slower the further they are from the Sun. But that's not what we see in galaxies. Instead, the rotation speeds of stars and gas in a galaxy remain constant, or even speed up the farther out they are from the center. To explain this strange observation, it seems clear that the distribution of mass in spiral galaxies is different from the solar system. Specifically, there may be a large amount of invisible, non-luminous matter, what we call dark matter, on the outskirts of the galaxy. In bound systems like galaxies, the stars are also governed by a rule called the virial theorem, which helps explain how mass is spread out in a system based on the speeds of the stars. When astronomers look at how fast stars are moving in systems like elliptical galaxies or dense star clusters, they can use this theorem to figure out how mass is distributed. However, in many cases, the measured speeds don't match what we'd expect based on the amount of visible mass in the system, even when we consider complex orbital patterns of the stars. Much like with the rotation curves of galaxies, the most logical explanation for this mismatch is that there's more invisible matter involved. Again, dark matter. Galaxy clusters are key to studying dark matter because we can measure their mass in 3 different ways. by looking at the range of speeds at which the galaxies in the cluster move, by studying the X-rays emitted by the hot gas inside the cluster. By analysing these X-rays, we can determine the temperature and density of the gas, which lets us calculate the pressure. Using the balance between gravity and pressure, we can figure out the total mass of the cluster. Through gravitational lensing, where the mass of the cluster bends light from more distant objects, this lets us measure the cluster's mass without needing to directly observe the motion of the galaxies. All three of these methods point to the same conclusion. Dark matter makes up roughly 5 times the mass of all the visible matter in these clusters. One interesting result of Einstein's theory of general relativity is a phenomenon called gravitational lensing. This occurs when massive objects, like galaxies or clusters of galaxies, sit between a light source and the observer. These massive objects act like a lens, bending the light that passes through them, making the light from the source appear distorted. The important thing to know is that gravitational lensing only requires the presence of mass. It doesn't matter what the mass is made of. The more massive an object is, the stronger the bending of light will be. For example, imagine a cluster of galaxies lying between a very distant object like a quasar and us. In this case, the galaxies in the cluster will bend the light from the quasar, making it look different. When we talk about strong lensing, we're referring to the dramatic way the light from background galaxies can be bent into arc shapes as it passes through a massive object's gravitational field. This has been observed around many distant galaxy clusters, including one known as Abel 1689. By studying the shape of these arcs, scientists can figure out the mass of the galaxy cluster causing the bending. In the weak lensing scenario, the bending is much less noticeable, and galaxies don't turn into arcs. Instead, we see tiny distortions in the shapes of galaxies. By looking at these slight changes, scientists can learn about how dark matter is spread out in the universe. The patterns of mass and light from these observations match what we expect from studies of dark matter. Now, while both dark matter and ordinary matter are forms of matter, they behave very differently. Early in the universe, ordinary matter was charged and interacted strongly with the light, which caused it to scatter. Dark matter, on the other hand, doesn't interact directly with light, but it still affects the universe in other ways. For example, it influences the cosmic microwave background, CMB, through its gravitational pull, especially on large scales. It also has an effect on the movement and density of ordinary matter. Because of these differences, ordinary matter and dark matter evolve in separate ways and leave distinct traces on the CMB. The CMB is very close to being a perfect blackbody, meaning it gives off a smooth, uniform temperature. However, there are tiny temperature differences, about 1 part in 100,000, that scientists can study. These small variations, called anisotropies, can be mapped out across the sky. When scientists break down this map into a graph called the angular power spectrum, they see a series of peaks that are evenly spaced but have different heights. The exact positions of these peaks depend on key factors in cosmology, and by comparing these positions to theoretical models, we can learn more about the universe's makeup. The first discovery of the CMB's anisotropies came in 1992 by the COBE satellite, but the resolution wasn't high enough to see the detailed peaks. In 2000, the Boomerang experiment, using a balloon to take measurements, found the first of these peaks. Later, the WMAP satellite and the Planck spacecraft measured these peaks much more precisely. Their findings supported the lambda CDM model of cosmology. Structure formation is the process that began shortly after the Big Bang, when small irregularities in the universe's density caused matter to collapse and formed stars, galaxies, and clusters of galaxies. Before this period, the universe was uniform, with no significant differences in density, as described by the Friedmann solutions to general relativity. Over time, tiny fluctuations in density started to grow and clump together, turning the smooth, featureless universe into a more complex structure filled with stars and galaxies. In the early stages, radiation dominated the universe and had a major impact on matter. This radiation prevented ordinary matter's density fluctuations from growing and forming structure. If the universe only had ordinary matter, these fluctuations would not have had enough time to evolve into the galaxies and clusters we see today. The key to solving this problem lies in dark matter, which is unaffected by radiation. This allowed its density fluctuations to grow first, creating gravitational wells that later helped ordinary matter collapse into galaxies and other structures. The gravitational pull from dark matter acted like a magnet, pulling in ordinary matter and speeding up the formation of these large cosmic structures. A striking example of the impact of dark matter is the Bullet Cluster, formed by the collision of two massive galaxy clusters. What makes the Bullet Cluster particularly interesting is the difference between where the mass of the cluster is located according to gravitational lensing, the bending of light around massive objects, and where the visible matter is found. This discrepancy is hard to explain with alternative gravity theories, which expect gravitational lensing to happen only around visible matter. However, the standard theory of dark matter can easily explain this. The visible gas in the clusters, which interacts with light and other forms of radiation, was slowed down and cooled by electromagnetic forces during the collision. Dark matter, on the other hand, doesn't interact with light in the same way, so it passes through the collision unaffected, separating from the visible gas. This created two distinct lensing peaks, as observed. In addition to dark matter, astronomers use Type Ia supernovae as standard candles to measure distances across the universe. These supernovae have a known brightness, so by measuring how dim they appear, scientists can calculate how far away they are. This method has revealed that the universe is expanding faster and faster, a phenomenon usually attributed to dark energy. Baryon acoustic oscillations, BAO, refer to regular fluctuations in the density of ordinary matter, baryons, in the universe, which occurred on large scales in the early universe. These oscillations were caused by sound waves travelling through the hot, dense fluid of photons and baryons before the universe cooled enough for atoms to form. The effects of these sound waves can still be seen in the cosmic microwave background, CMB radiation. As the universe expanded, dark matter and ordinary matter began to clump together, but the effect of the original oscillations weakened over time. However, we can still observe a slight preference for galaxies to be separated by about 147 million light-years, which is a subtle but measurable signature of these early oscillations. This pattern was predicted in the 1990s and confirmed in 2005 through large galaxy surveys like the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey. By combining CMB observations with BAO measurements, scientists can get a precise estimate of important cosmic values, such as the rate of expansion of the universe and the amount of matter it contains. These results support the lambda CDM model, which is the current leading theory of cosmology. Large surveys of galaxy redshifts can help us create a three-dimensional map of how galaxies are spread out in the universe. However, these maps are not perfect because the distances we estimate are based on the redshift we observe. The redshift we measure is affected by two things. The main factor is the universe's expansion, but there's also a smaller influence from the galaxy's own motion, known as its peculiar velocity. In general, superclusters, groups of many galaxies, are growing more slowly than the average expansion of the universe because their gravity is pulling things together. On the other hand, voids, vast empty spaces between galaxies, are expanding faster than the universe as a whole. This difference in expansion causes some interesting effects. For example, galaxies that are located in front of a supercluster are moving toward it faster than expected, so their redshift will be a little higher than we would normally calculate for their distance. Conversely, galaxies behind the supercluster appear to have a slightly lower redshift than expected. This difference causes superclusters to look squashed along the line of sight, while empty spaces look stretched. However, this effect is hard to notice in a single structure since we don't know its exact shape. Instead, scientists can see this effect by averaging information from many structures. The event was first guessed by Nick Kaiser in 1987 and was later proven in 2001 by the 2DF Galaxy Redshift study, with results matching what we expect from the lambda CDM model of the universe. In a connected area of study, the Lyman alpha forest means the group of absorption lines found in the light patterns of faraway galaxies and quasars. These lines are made by plain hydrogen blocking light at a certain wavelength called the Lyman alpha change. Looking at the Lyman alpha forest helps space scientists test and improve universe models, with results that match with findings from the WMAP data. Dark matter is often sorted into three kinds: cold, warm, and hot, These names don't mean temperature, but instead show the speed at which the pieces were moving in the early universe. In simple words, they tell how far the pieces moved around randomly before the universe started growing and slowed them down. This distance is called the free streaming length, FSL. The grouping of dark matter depends on how this FSL matches the size of a young galaxy, an early space object that would later become a small galaxy. If the FSL is much smaller than the size of a young galaxy, it's called cold dark matter. If it's about the same size, it's warm dark matter, and if the FSL is much bigger, it's hot dark matter. There are also ideas that say a mix of these types exists, which were more liked in the middle of the 1990s, but became less liked after the finding of dark energy. The main idea behind the free streaming length is that, after the Big Bang, the universe began with small changes in how thick matter was, which were caused by tiny changes at the smallest levels. As these pieces moved from thicker areas to thinner ones, the fast growth of the universe put a limit on how far they could go. Faster pieces, like those in hot dark matter, could go farther before the universe grew too much, while slower pieces, like those in cold dark matter, couldn't go as far. This means that the free streaming length sets a limit on the size of things that could form in the early universe. Hot dark matter would lead to the forming of big things, like superclusters, which would later break into galaxies. On the other hand, cold dark matter allows for smaller things, like galaxies, to form first. Newer views, especially deep space pictures of the universe, show that galaxies were the first to form, followed by groups and superclusters as galaxies came together. This backs the idea that most dark matter is cold, not hot. This is also why neutrinos, which move almost as fast as light and would be hot dark matter, cannot make up most of dark matter. Dark matter means any kind of matter that acts with visible matter, like stars and planets, mostly through gravity. This means that dark matter might not be a totally new kind of piece, but could, in theory, include normal matter like protons or neutrons. In fact, many things known to space scientists, such as planets, brown dwarfs, red dwarfs, stars, white dwarfs, neutron stars, and black holes, belong to this group. For example, when a black hole pulls in matter, it doesn't tell regular matter, like protons, apart from other kinds of matter. Once it's inside the event horizon, all matter is treated the same. These hard-to-find objects are grouped together as MACHOs, massive compact halo objects. Some scientists once thought that MACHOs made up most of dark matter, but this idea has since been mostly left behind. There is strong proof saying that most of dark matter is not made of normal, visible matter. First, if there were enough regular matter like gas or dust spread around, we would be able to see it when it shines by light from stars. But we don't see this kind of matter in the amounts we would expect. Next, the Big Bang idea helps us understand how the elements we see today were made. According to this idea, if there were more normal matter, called baryons, in the early universe, we would have seen more elements like helium, lithium, and other heavier elements. Based on what we see, we know that only about 4 to 5% of the universe's total mass is made of this regular matter. But big studies of galaxies and other space structures show that the total amount of matter is about 30% of what is needed to keep the universe balanced. More studies have shown that only a small part of dark matter seems to be in the form of normal, hidden objects, like small planets or black holes, called MACHOs. Studies using the bending of light by gravity, gravitational microlensing, show that these objects can't make up most of dark matter, as their masses fall within a range that leaves out almost all of the likely options. Careful studies of the space microwave background, the faint light left over from the Big Bang, by projects like WMAP and Planck, give strong proof that about 5/6 of the matter in the universe doesn't act much with light or regular matter, except through gravity. This shows that dark matter is mostly invisible, and can only be found by how it pulls on other things with gravity. If regular matter, called baryonic matter, doesn't make up most of dark matter, then dark matter must be made of something else, mainly non-baryonic matter. There are two main choices for non-baryonic dark matter: new, strange pieces, and old black holes from the early universe. Unlike baryonic matter, these non-baryonic pieces don't help make the elements that formed during the Big Bang, a process called Big Bang nucleosynthesis. Instead, we only see them because of the gravity effects they cause, like how they bend light, called weak lensing. Some kinds of dark matter can even act with each other, self-acting dark matter, or with regular pieces like WIMPs, weakly interacting massive particles. These actions might give off signs like gamma rays and neutrinos, which scientists might be able to see, indirect finding. There are many different choices for what dark matter could be, each with good and bad points. WIMPs don't have a strict meaning, but they are mostly thought of as basic pieces that act through gravity, and maybe other weak forces like the weak nuclear force. Many ideas say that WIMPs were made in the early universe, in a way like how regular pieces were made. These pieces would make up what's called cold dark matter. To explain how much dark matter we have today, the WIMP pieces would need to destroy each other in a certain way, which matches what would happen if they had masses around 100 giga-electron-volts and acted through the electroweak force. This idea is often referred to as the WIMP miracle, because it fits so well with predictions from supersymmetric theories, which extend the standard model of particle physics. A stable partner particle from supersymmetry has long been seen as a prime candidate for dark matter. Researchers are working hard to find WIMPs by looking for the products of their annihilations, such as gamma rays, neutrinos, and cosmic rays coming from nearby galaxies. They also use experiments designed to directly detect WIMPs in laboratories by measuring their interactions with atomic nuclei, or by trying to create WIMPs in particle colliders like the Large Hadron Collider, LHC. However, in the early 2010s, experiments didn't find strong evidence for supersymmetry, and the LHC results cast doubt on the simplest WIMP ideas. Axions, another candidate for dark matter, are theoretical particles that were first proposed in 1978 by Frank Wilczek and Steven Weinberg. These particles were originally suggested to solve a problem in the theory of quantum chromodynamics, QCD, which explains how quarks and gluons interact. Axions are incredibly light and weakly interact with other particles, making them a perfect candidate for dark matter. They could be produced in the early universe and would remain present today, their abundance depending on their mass. Axions are thought to be so light that they could help explain some of the small-scale issues in the lambda CDM model, the leading cosmological model. The axion theory has gained traction in recent years, especially after WIMPs were not detected. The axion's extremely low mass means that quantum effects could potentially explain the small-scale mysteries of dark matter. Primordial black holes, another intriguing idea, are thought to have formed in the very early universe, right after the Big Bang. During the period of rapid expansion known as inflation, incredibly dense regions of subatomic matter could have collapsed under their own gravity, creating black holes without the need for a star's death, as is the case with regular black holes. These black holes would predate the formation of the first stars and could have masses ranging from tiny, even as small as atoms, to incredibly large, far beyond typical stellar black holes. The concept of primordial black holes was first suggested in 1967 by Yakov Zeldovich and Igor Novikov, and later by Stephen Hawking in 1971. The idea quickly gained traction as a potential explanation for dark matter. One of the advantages of primordial black holes as dark matter candidates is that the theory behind black holes is already well established in physics, general relativity, and black holes themselves are already known to exist. However, creating primordial black holes might require complex conditions, such as exotic cosmic inflation or theories beyond the standard model of particle physics. In 2015, gravitational wave measurements from the detection of black hole mergers sparked renewed interest in primordial black holes as dark matter. Some black holes detected by these experiments had masses that seemed too large to be formed by the usual processes, like the collapse of a star. This suggested they could be primordial. However, a study that looked for signs of gravitational lensing from intermediate mass black holes, expected to be dark matter, found no evidence for them, although some researchers suggest this could be due to assumptions about the mass of these black holes. Further observations, like those made by the James Webb Space Telescope, may provide more clarity on this theory. Scientists once thought that incredibly small black holes, known as primordial black holes, might make up a significant portion of dark matter. However, the Voyager 1 spacecraft, which explored beyond the Sun's influence, measured the flow of positrons and electrons and found something surprising. The amount of particles detected was too low, and their energy levels were not what scientists expected. This led researchers to conclude that these tiny black holes are too rare to account for dark matter. Despite this, the idea of dense forms of dark matter continues to be researched, with new theories even suggesting ways to cool dark matter. As of 2018, the mystery remains unsolved. In 2019, further observations of the Andromeda Galaxy showed no signs of microlensing effects, which would be expected if tiny black holes were present, adding more doubt to their existence. However, there's still a gap in our understanding. There is a range of mass smaller than what we can currently detect with optical microlensing, where primordial black holes could potentially make up all of the dark matter. This area remains open for exploration and continues to challenge our understanding of the universe. If dark matter is made of particles that barely interact with anything, an important question arises. Could these particles form objects like planets, stars, or black holes? Historically, the answer has been no, and there are two key reasons for this. It can't easily lose energy. Regular matter forms dense objects like stars and planets because it can lose energy in many ways. For example, when particles fall inward due to gravity, they can lose energy, which allows them to slow down and condense into more stable objects. Dark matter, however, doesn't seem to have the ability to lose energy because it doesn't interact with other matter strongly, except through gravity. Without ways to release energy, dark matter particles that start to get pulled inward would just heat up, speed up, and eventually escape, preventing the formation of compact objects. It doesn't interact in diverse ways. Regular matter interacts through multiple forces, such as gravity, electromagnetism, and the strong nuclear force, allowing it to form complex structures like atoms, stars, and galaxies. For instance, inside stars, particles interact through nuclear fusion, emitting light and neutrinos. In dark matter, we don't see evidence for such interactions beyond gravity, and possibly some weak interactions, but this is still speculation. Without these varied interactions, dark matter doesn't have the ability to form the kinds of structures that regular matter does. If dark matter is composed of subatomic particles, these particles pass through every square centimetre of Earth millions or even billions of times every second. Many experiments are trying to test this idea, while WIMPs, weakly interacting massive particles, have been the most commonly searched for candidates. Axions are also getting attention, especially with projects like the Axion Dark Matter Experiment, ADMX. Other possibilities include heavy particles from a hidden sector that only interact with regular matter through gravity. There are two main types of experiments investigating dark matter: direct detection experiments. These look for signs that dark matter particles are scattering off atomic nuclei in a detector. The goal is to measure tiny energy shifts, a few keVs, caused by these interactions. When dark matter hits an atom, the atom might release energy in the form of light or vibrations, which can be detected. To do this well, these experiments need to be as isolated as possible from background interference, which is why they are often conducted deep underground, where cosmic rays don't interfere. Notable underground labs include Storwell Mine, Sudan Mine, and the Gran Sasso National Laboratory. These experiments often use two technologies: cryogenic detectors that measure heat from particle collisions in materials like germanium, noble liquid detectors that detect light produced when a particle hits liquids like xenon or argon. Some prominent experiments in these areas include CDMS, CREST, xenon, and LUX. These detectors are particularly good at distinguishing dark matter from background particles, which mostly scatter off electrons, while dark matter particles scatter off atomic nuclei. Indirect detection experiments. These look for the after effects of dark matter particles annihilating or decaying. There's currently no confirmed detection of dark matter in direct detection experiments, but these efforts have helped narrow down the possible properties of dark matter particles. One interesting claim comes from the DAMA, NE, and DAMA Libra collaborations, which have noticed a yearly fluctuation in their data, possibly due to the Earth's motion through the dark matter halo. However, other experiments such as LUX and super CDMs have not observed the same effect, creating a bit of a mystery. There are also special experiments with directional sensitivity, which track the motion of dark matter particles based on the solar system's movement around the galactic center. This technique tries to separate dark matter signals from background noise, which should be evenly distributed. These experiments, such as DMTPC and drift, attempt to detect the direction in which dark matter is moving to help identify potential signals. Indirect detection experiments aim to find signs of dark matter by looking for the products that emerge when dark matter particles self-destruct or decay in space. In certain regions with high concentrations of dark matter, like the center of the Milky Way, two dark matter particles might collide and annihilate each other, releasing gamma rays or pairs of normal particles and their opposites, antiparticles. Alternatively, if a dark matter particle is unstable, it might break down into standard particles or others, which could be detected indirectly through an unexpected surge of gamma rays, antiprotons or positrons, coming from areas with a lot of dark matter, like the Milky Way's core or distant galaxies. One of the challenges of this kind of search is that other cosmic events could produce similar signals, so multiple signals from different sources are needed to confirm a dark matter discovery. Dark matter particles that pass through the Sun or Earth might interact with atoms and lose energy in the process. This could cause dark matter to accumulate at the centers of these celestial bodies, increasing the chances for collisions or annihilation. These events could send out a unique signal of high-energy neutrinos, which could serve as strong evidence of dark matter made of WIMPs, weakly interacting massive particles. Instruments like Amanda, IceCube and Antares are actively searching for this signal. In addition, the detection of gravitational waves by LIGO in 2015 opened the door for observing dark matter in new ways, especially if it exists as primordial black holes. Several experiments have tried to detect dark matter emissions, such as those from annihilation or decay. For example, the Energetic Gamma Ray Experiment Telescope spotted more gamma rays in 2008 than expected from the Milky Way, but scientists believe this was due to errors in estimating the telescope's sensitivity. The Fermi Gamma Ray Space Telescope is continuing this search, and in 2009, it observed a puzzling excess of gamma rays from the center of the Milky Way. This could be a sign of dark matter annihilation or an unknown group of pulsars. In 2012, a deeper analysis of Fermi data suggested a 130 giga-electron-volts signal from the Milky Way's core, which was interpreted as a possible result of WIMP annihilation. At even higher energies, ground-based telescopes have set limits on dark matter annihilation in dwarf galaxies and galaxy clusters. The Pamela experiment, launched in 2006, detected an unusual amount of positrons, which might come from dark matter or pulsars, though no similar excess of antiprotons was found. Similarly, the Alpha Magnetic Spectrometer aboard the International Space Station observed high-energy cosmic rays in 2013, possibly linked to dark matter annihilation. One exciting way scientists are trying to solve the mystery of dark matter is by attempting to create it right here on Earth, inside powerful labs. At massive research facilities like the Large Hadron Collider, often called the LHC, scientists smash protons together at incredibly high speeds. These collisions might create dark matter particles, even if only for a moment. But since dark matter doesn't interact much with normal matter and can't be seen directly, researchers look for clues in a different way. Imagine watching a juggler throw 10 balls into the air, but only seeing 8 come down. Something's missing. In the same way, scientists carefully measure all the particles that fly out from a proton collision. If the numbers don't add up, if some energy or motion seems to vanish, it could mean a dark matter particle was created and slipped away unnoticed. A similar idea was used in an earlier experiment called LEP, which looked at how dark matter might interact with electrons. Even though neither experiment saw dark matter directly, both helped scientists set limits on what dark matter might be like, how strong or weak its interactions are. But no matter how promising a lab discovery might seem, it isn't enough on its own. To prove that a new particle is truly dark matter, scientists need to compare lab results with what they find in space. That means using both direct detection, looking for dark matter here on Earth, and indirect detection, looking for its effects in space to confirm the find. Because dark matter still hasn't been clearly found, many other ideas have popped up to explain the strange things we see in the universe, like the way galaxies spin, or how light bends around huge clusters of matter. Much of the evidence for dark matter is based on a famous theory called general relativity, which was developed by Albert Einstein. This theory works very well when it's tested in our solar system, but we're not entirely sure it works the same way on the much larger scale of galaxies and the whole universe. So, some scientists have suggested changing general relativity to explain what we see, without needing dark matter at all. These new theories go by names like Air-Onde, short for modified Newtonian dynamics, TVES, which adds relativity to Meond, FR gravity, dark fluid theory, negative mass, and entropic gravity. Each of them offers a different twist on how gravity might work. However, there's a big challenge. The evidence for dark matter doesn't come from just one place, it comes from many different kinds of observations. While some of these alternative theories might explain one or two things, they struggle to explain everything. It's like trying to fix a leaky boat by plugging one hole, only to have water start pouring in from another. Still, a few of these ideas have shown promise. In the year 2016, a test involving gravitational lensing, a bending of light caused by gravity, gave some support to entropic gravity. And in the year 2020, an observation backed up Mond. But even with these small wins, most scientists believe the full picture still points toward the existence of dark matter. They think that while changing the laws of gravity might help explain part of the mystery, something real, something invisible but powerful, is still out there, shaping the universe from the shadows. In the study of the universe, dark energy is a strange kind of energy that affects the universe on the bigger scales. Its main job is to speed up how fast the universe is growing. If our current understanding of how the universe works is correct, dark energy makes up about 68% of all the energy in the universe today. In comparison, dark matter makes up 26%, and regular matter is only about 5%. Other types of energy, like neutrinos and photons, are almost too small to count. Even though dark energy has a very low density, about 7 times 10 to the power of minus 30 grams per cubic centimetre, which is much smaller than the density of a normal matter or dark matter, it still controls most of the universe's energy because it is spread out evenly across space. Scientists first started to think dark energy might be real after looking at the light from faraway supernovae. Type Ia supernovae are very helpful for measuring distances because they shine with the same brightness. By comparing how bright they look to how much their light has been stretched, which tells us how fast they're moving away, scientists found out that the universe is growing faster and faster, instead of slowing down as they once believed. Before this discovery, scientists thought gravity from all the matter and energy in the universe would slowly make the expansion slow down. Since this surprising discovery, many pieces of evidence have continued to support the idea that dark energy is real. Even though scientists have found signs of dark energy, they still don't fully understand what it is. A few ideas try to explain it. One idea is called the cosmological constant, which says that dark energy is a steady and unchanging energy that fills space evenly. Another idea is called scalar fields, which are energy sources that change with time and space, like quintessence or modulars. The cosmological constant would stay the same everywhere and all the time, but scalar fields could change. There are other ideas too, like interacting dark energy, which means dark energy could be affected by other forces, and cosmological coupling, which suggests dark energy might connect with gravity in ways we don't yet understand. The cosmological constant is a term that can be added to Einstein's equations in general relativity. When treated as a source in these equations, it acts like the energy of empty space, also called vacuum energy. This energy can be either positive or negative, depending on how it is understood. Einstein first added the cosmological constant to make his equations describe a universe that didn't change over time. He thought this constant would act like a force that balanced gravity, using a kind of dark energy to keep everything from falling together. He used the capital Greek letter lambda to stand for this idea. Einstein said that empty space could behave like it had negative mass, spread out through all of space, helping to stop the universe from collapsing. But this idea turned out to be unstable. Even a tiny change in the size of the universe would cause it to either grow without stopping or shrink without end. In Einstein's plan, the universe wasn't truly balanced. If the universe grew just a little, it would create more vacuum energy, which would speed up the expansion. If it shrank, it would keep collapsing. Einstein also thought that empty space might have its own energy, which would not get weaker as space got bigger. As the universe expanded, this energy would stay the same, which would speed up the universe's growth. This kind of expansion happens because matter is not spread out evenly across the universe. In 1929, Edwin Hubble's work showed that the universe was not staying the same. It was actually getting bigger. This made Einstein say that his earlier belief in a universe that never changed was his biggest mistake. In 1980, Alan Guth and Alexei Starobinsky came up with an idea about the early universe called cosmic inflation. They said that a powerful force like dark energy caused the universe to grow extremely fast right after the Big Bang. This fast growth, called inflation, is now a major part of our current ideas about how the universe began. But the energy that caused inflation was much greater than the dark energy we see today. How inflation and today's dark energy are related is still a puzzle. Once inflation became a widely accepted idea, the cosmological constant seemed less important for a while. In the 1980s, most scientists studied models of the universe that had mostly cold dark matter and a small amount of regular matter. These models seemed to match what we saw when galaxies formed, but they didn't explain everything. For instance, they predicted a lower value for the Hubble constant than what was actually measured. They also had trouble explaining huge galaxy groups. These problems got worse after the 1992 discovery of uneven patterns in the cosmic microwave background by the COBE spacecraft. New models were created, like the lambda CDM model, which includes the cosmological constant. In 1998, scientists looking at faraway supernovae found that the universe's growth was speeding up, which gave the first strong proof for dark energy. Not long after that, more results backed up the idea of dark energy. In 2000, the Boomerang and Maxima experiments studied the cosmic microwave background and found that the total energy in the universe was almost exactly what's needed to keep it flat. In 2001, the 2-degree field galaxy redshift survey showed that matter made up about 30% of this energy. The rest was explained as dark energy. Better measurements from the WMAP satellite taken between 2003 and 2010 kept supporting the lambda CDM model, giving a clearer view of what the universe is made of. The term dark energy was first used in 1998 by Michael S. Turner, borrowing from the earlier idea of dark matter, first mentioned by Fritz Zwicky in the 1930s. To really understand how the universe grows over time, scientists need to measure this expansion very carefully. In general relativity, we figure out how fast the universe grows by looking at its shape and using a key formula called the cosmological equation of state. This formula links temperature, pressure, and the mix of matter, energy, and vacuum energy in any part of space. One of the biggest goals in today's study of the universe is to measure the equation of state for dark energy. This is one of the hardest problems in the field. When scientists add the cosmological constant to the standard model of the universe, the FLAW metric, they get the lambda CDM model. This model is often called the standard model of cosmology because it matches what we see in space so well. Since 2013, this lambda CDM model has been confirmed by many new and accurate measurements, including data from the Planck spacecraft and the Supernova Legacy Survey. Early results from the survey showed that dark energy acts on average just like Einstein's cosmological constant, with about 10% accuracy. Newer findings from the Hubble Space Telescope's Higher Z team suggest that dark energy has existed for at least 9 billion years, even before the universe's expansion started speeding up. Even with all this data, we still don't really know what dark energy is. It seems to be very smooth and spread out evenly across space, with very little mass, and it doesn't seem to interact with any known forces except gravity. Its tiny mass, about 10 to the power of minus 27 kilograms per cubic meter, means it's probably too weak to be found in laboratory tests. But even though it's so light, dark energy still makes up about 68% of the total energy in the universe because it fills all the empty space and has a strong effect on how the universe grows. One leading idea connects dark energy with vacuum energy. Vacuum energy comes from tiny particles, and their opposites, that are always popping in and out of existence in empty space because of Heisenberg's uncertainty principle. This constant change in energy is often believed to be a main part of what makes dark energy work. According to Einstein's theory of relativity, this vacuum energy should have gravity effects too. That means it adds to the cosmological constant, which helps explain why the universe is expanding faster. But there's a big problem. The amount of vacuum energy predicted by quantum theory is way bigger than what we see, and scientists are still trying to solve this mismatch. No matter what dark energy really is, it must have a very strong negative pressure to explain why the universe is expanding faster. In general relativity, pressure affects gravity just like mass does. Both pressure and mass are part of something called the stress-energy tensor, which shows how matter affects gravity. When applied to the universe, this negative pressure causes it to grow faster. If the universe were shrinking, the pressure would slow down that shrinking. This speeding up is sometimes called gravitational repulsion, because it seems to push the universe apart instead of pulling it together. As we currently understand it, the universe has three main parts: matter, radiation, and dark energy. Matter is anything that has mass or takes up space, and as the universe grows, the energy from matter gets thinner in a way that depends on how much space there is. For example, if you have a box with particles inside and you double the size of the box, the energy from those particles goes down by 8 times, because they spread out in 3 directions, so the energy per unit of space drops. Radiation, like light or heat, behaves differently. Its energy drops even faster than matter when space gets bigger. This is because the energy spreads out, and the light also gets stretched, redshifted, which makes it lose energy faster than matter does. Dark energy is different. It doesn't care how big space gets. It stays the same. It's part of space itself. No matter how much the universe grows, dark energy doesn't thin out or weaken. It keeps pushing the universe to grow faster. The proof for dark energy, even though it's not direct, comes from many different sources that all point to the same idea: distance and redshift measurements. By comparing the distances to faraway objects with how stretched their light is, scientists found that the universe has grown more in recent times than it did earlier. This means something, like dark energy, must be causing this faster growth. The need for extra energy. The universe looks flat, not curved, which means there has to be some extra kind of energy besides normal matter and dark matter. Dark energy helps explain why the universe looks this way. Cosmic density waves. Looking at how matter is arranged on large scales in the universe gives more clues. The patterns of galaxies and other objects also suggest that dark energy is real. In 1998, a group of astronomers called the High Z Supernova Search Team studied Type Ia supernovas and found something surprising. The universe's expansion was speeding up. Another group, the Supernova Cosmology Project, found the same thing in 1999. For their work, the scientists won the Nobel Prize in Physics in 2011. Since then, many different observations have supported these results. Data from the cosmic microwave background, leftover light from the Big Bang, light bending caused by gravity, called gravitational lensing, and the shape of the universe all agree with the idea of dark energy, just like the Lambda CDM model predicts. Some critics think only redshift and distance data really prove dark energy. But even patterns in the cosmic microwave background show that the universe is growing faster than it would without dark energy. Supernovae are incredibly important in the study of the universe because they work like standard candles. That means scientists know how bright they are supposed to be. By looking at how bright they appear from Earth, astronomers can figure out how far away they are. This helps them measure how fast the universe is expanding. One special kind of supernova, called Type Ia, is especially useful because it always shines with nearly the same brightness. This makes it one of the most dependable tools for measuring distances in space. New data shows that dark energy makes up about 71.3% of the entire universe. The rest is made of dark matter and regular matter. The leading theory about how galaxies and stars form also supports this idea. It says that all the matter we can see, plus dark matter, adds up to only 30% of the total energy needed to make the universe flat. which means its shape is balanced and not curved too much one way or another. In the year 2011, the Wigglesy Galaxy Survey gave us more clues. Scientists studied more than 200,000 galaxies and used a smart method to measure distances to galaxies as far as 2,000 million parsecs away. What they found backed up the idea that the universe's expansion is speeding up over time. Strong proof that something is pushing everything apart faster and faster. For the universe to be flat, as it seems to be, there must be more than just matter. The visible matter and dark matter together only make up 30% of what's needed. So, the remaining 70% must be something else, most likely dark energy. Observations from a space mission called the Wilkinson Microwave Anisotropy Probe, WMAP, found that about 72.8% of the universe is made up of dark energy. Later, more accurate data from the Planck spacecraft revised this number to 68.3% dark energy, 26.8% dark matter, and just 4.9% regular matter. Dark energy also helps explain strange patterns seen in the cosmic microwave background, the faint glow left over from the Big Bang. When particles of light, called photons, pass through areas with strong gravity, like big clusters of galaxies or empty spaces between them, they lose or gain energy. This creates tiny hot and cold spots in the background light. This effect is known as the integrated Sachs-Wolf effect and gives scientists another clue that dark energy exists. A newer way to measure dark energy involves something called the Hubble constant, which tells us how fast the universe is expanding at different times. Scientists do this by studying old galaxies that haven't changed much over time. These galaxies are like cosmic clocks. By checking their age and how much their light has been stretched, researchers can figure out how fast the universe was expanding in the past. Even though we've learned a lot, dark energy is still one of the biggest mysteries in all of science. Most scientists agree that it is a force that's pushing the universe to expand faster, but no one knows exactly what it is or how it works. That's why researchers are exploring many different ideas. Some are checking if Einstein's famous theory of gravity might need updating. Others are trying to find out the exact nature of dark energy. Still, others are looking for totally new explanations based on what we see in space. One simple idea is that dark energy is just part of space itself. In this view, even empty space has energy in it, called vacuum energy. This idea is known as the cosmological constant and is represented by the Greek letter lambda. It's a big part of the leading model scientists use to explain the universe, known as the lambda CDM model. Because energy and mass are connected, as Einstein showed, this vacuum energy would have gravity and could affect how the universe expands.